Okay, today we're going to go over the acid-base homework that you had. There's only one thing that I wanted to point out. A couple people had that wrong. Today we're going to be learning about titrations. That's going to be the last thing in this unit. For homework, I'll show you the sheet. You should have it in your packet already, but it's a titration worksheet, and then it's going to be due by noon tomorrow. And test tomorrow, the buses will be sending out packets that I've put together for the next unit. The next unit is on organic chemistry. It's typically 3 weeks long. So we'll just continue with learning with the organic chemistry, which is the next thing. The test will come home with the packet. I'm going to make it due Thursday at noon, and I'm going to put a Google Forms together so people don't just take a picture and then send it in. You fill in the answers. It's going to be mostly multiple choice, so you just select the right one on the Google form, and then it will send directly to me, and then I can grade it that way. Okay, so first let's take a look at some of the highlights of that homework. Most of these were fine. The only thing that was probably an ongoing issue was this one. Name one example of a substance that will react with Pb, which is lead, to liberate H2. Remember that if we are looking on our CRT, which is, we'll see table J here, we looked at this a couple times, that anything above H2, anything above hydrogen gas, will displace hydrogen gas, and then hydrogen gas will come out of solution. So lead is something that will displace hydrogen gas, but the source of hydrogen gas is going to be an acid. So all these things, when they're mixed with acids, will kick hydrogen out. Remember, copper, silver, and gold, those three are not more reactive than H2. Therefore, if you mix them with acids, they won't kick hydrogen out. So essentially, pick an acid. Name one example, pick an acid. Hydrochloric, sulfuric, nitric, any of those will react with lead or anything above H2 on table J, and then push out hydrogen gas. The rest of these were pretty good. All water-soluble acids will produce hydronium ions. That was also in your notes, and that was it for that one. So I wanted to highlight that. The next thing is notes on titrations. There is a video from Professor Dave about titrations. I will post it, but I think if you have this digitally that I put on the classroom, if you click on that, it should be able to send you there. If not, I'll post it anyway. So titration is a technique used to determine the acidity of a solution. I was waiting for that because I knew it was going to happen. For the acidity. You can actually calculate the basicity, how basic something is, but it's basically figuring out what the acidity, most of the times for the acidity of whatever the solution is. So here's the method. A known volume of one substance is placed in an Erlenmeyer flask. Just to remind you, this is an Erlenmeyer flask. A few drops of an appropriate indicator, such as phenolphthalein, are added to the Erlenmeyer flask. The solution of unknown concentration is placed in a burette with a T. This is a burette over here. I'll pull it over here in a second. It's a device that can deliver very precise volumes of a solution, and I'll show you how that works digitally. There's a simulation that we're going to use for a lab. The initial volume reading on the burette is taken. The unknown solution is added to the Erlenmeyer flask until the two reactants have been combined in the stoichiometric ratio, which is the ratio given by the chemical equation. In other words, if I've got hydrochloric acid and I combine it with sodium hydroxide, you know what's going to happen here. Acid, base, what do we get? A salt, which would be sodium chloride, and water. So the stoichiometric ratio is 1 to 1. 1 mole of hydrochloric acid for every 1 mole of NaOH. That's the ratio given, okay? So this point is called the equivalence point. So when I've added enough base to neutralize the acid that I have in the Erlenmeyer flask, it will reach what's called the equivalence point. At that point, if it's a good indicator like phenolphthalein, it should change color. The point at which the indicator changes color is called the end point. So there's the equivalence point when it just starts, and then the end point. And in this case, they're going to be the same. So in other substances, it might be different. But for this, the equivalence and the end point are the same. The final volume on the reading on the burette is taken. You find how much you've added, and then you can figure out what the acidity is. The solution with the known concentration is called the standard solution. So that means I've got to know exactly what the molarity of the base is that I'm adding to the acid. If I don't know, then I've got two unknowns and I can't figure it out. The indicator is one color in the presence of the acid and changes when it is neutral. So when it becomes neutral, it changes color. That's the case with with phenolphthalein. The end point is when enough acid has been added to completely neutralize the base, or vice versa. In the lab that we're going to simulate, we're going to be adding base to the acid. Since there are equal numbers of hydrogen and hydroxide needed for exact neutralization to occur, 1 mole for every 1 mole of hydroxide, we end up getting water. Therefore, the unknown molarity can be calculated from the final relationship. And this is in your CRT. I can show you here in a minute. It's basically the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And here's an example. It takes 83 milliliters of a 0.45 molar sodium hydroxide solution to neutralize 235 milliliters of an HCl solution. What is the concentration of the HCl solution? Of course, you would always start by putting your equation and what is given here. They're looking for what is the concentration of the HCl, which is the acid. That's my unknown. The volume of the acid is 235. And it takes 83 milliliters to neutralize it. That's the volume of the base. And the molarity of the base is 0.45. So once you punch all those in, the milliliters will cross out, and then 0.45 will be over those two, and you get an answer of 0.16 molarity. Okay, that's moles per liter, just to remind you. All right, let's take a look at the questions on the homework. If it takes 54 milliliters of a 0.1 molar NaOH to neutralize 125 mils of hydrogen chloride solution, what is the concentration? So I'll give you the first one. MAVA equals MBVB. if it takes 54 milliliters of the base to neutralize how much acid, what is the concentration of HCl? Concentration of the acid is my unknown. I'm neutralizing 125 milliliters, oops, it's a 5, of the acid. It takes 54, so that's my volume, of 0.1. And 54 milliliters. Molarity of the acid is that times that, which is 5.4 moles times milliliters over 125 milliliters. I can cross out my milliliters, and then my answer, once I punch it into my calculator, is going to be 0.043. And that is its molarity, moles per liter. Okay? The rest of these are pretty straightforward. They're pretty straightforward. Okay? So complete that. That's going to be due by tomorrow at noon. So it would really help a lot if you would put stuff on Google Classroom, if you can, versus emailing me a Google Doc. I think you can add a Google Doc pretty easily. Okay? And that's that. Now the other thing that I wanted to show you today was this simulated lab. Got about 3 minutes, see if we can do it. I'll probably make another quick video because we're actually going to do a lab on it. But this, I will send you the link to this. In this, I'm going to sit at the chair to fill all these in. But basically, you've got a type of reaction, and we'll put strong acid versus strong base because that'll change. We don't have to worry about why. This is the burette. You can spell it 2 different ways. This is the French spelling. We're going to fill the burette with base. The third thing we do is we choose the acid and the base. Let's choose hydrochloric acid and sodium hydroxide because that's what we would actually do in the lab if we were to do this. And the last thing to do is, we've got select the indicator. We're going to choose phenolphthalein because we're familiar with that, somewhat familiar. And then, and this is the tough part because you might flub this up. You've got to be careful. I have to take this and add little by little. And if you look down here, you'll see that at some point it's going to start turning it pink. So when it starts turning, did you see that? Now if I put too much in here, it's going to ruin it. So I'll put a little bit more, ruined. Okay, so I would have to reset this, do it again. I'm going to put base in here, acid, hydrochloric and sodium hydroxide using phenolphthalein. And then these numbers change down here. Okay? So in this case, we're figuring out the molarity of the base. And we'll do that calculation when I show you the other video. So essentially, when you get close, you just have to kind of fiddle around with this a little bit. There. Now that would be pretty close. So if I do dropwise, it's just, look at that, 1 drop was enough to change it to the last point. So you want it to get it to be pink, a light pink, permanently. All right, I'll make another video on this and then we'll do that actually as a lab.